Hello and welcome to G Fun Facts Online. Today, we're taking a journey to a place more remote than the deepest ocean trench and hotter than the surface of some stars. We're going deep, deep inside our own planet, to a mysterious borderland that holds the secrets to Earth's violent birth and its dynamic present. Forget what you learned in basic geology class because we're exploring the D-double prime layer. So what is this enigmatically named D-double prime layer? Imagine you could travel 2,900 kilometers straight down. You'd pass through the crust, then the vast mantle, and you'd finally arrive at the edge of the Earth's liquid iron-nickel outer core. This boundary zone, about 200 to 300 kilometers thick, is the D-double prime layer. It's the most significant dividing line inside our planet, separating the slowly churning solid rock of the mantle from the scorching, liquid metal of the core that generates our magnetic field. The temperature here skyrockets to around 4,300 Kelvin. But what really makes this layer fascinating for geoscientists is its sheer weirdness. It's not a smooth, uniform boundary. It's wildly patchy and uneven, almost like a landscape of buried continents. When scientists send seismic waves through it, our version of an ultrasound for the planet, the waves behave erratically, sometimes slowing down dramatically, other times speeding up for no apparent reason. For decades, this has been one of Earth science's greatest puzzles. So where did this lumpy, unpredictable layer come from? Cutting-edge research suggests we need to look back 4.5 billion years to the very birth of our planet. The leading theory is the giant impact hypothesis, which says a Mars-sized planet named Theia slammed into a young Earth. This cataclysmic event melted the entire planet, creating a global ocean of magma. Now, scientists believe a surprising ingredient was present at the bottom of this magma ocean: water. Under the immense pressure and heat, this water reacted with minerals to form a strange iron-rich compound called iron magnesium peroxide. This heavy iron-loving substance would have sunk and pooled at the very base of the solidifying mantle, creating thick, iron-rich patches. If this is true, the weird landscape of the D-double prime layer isn't just random. It's a preserved chemical fossil from Earth's ancient magma ocean, a direct message from our planet's chaotic infancy. This ancient origin story also helps solve another mystery. Why do seismic waves sometimes speed up when passing through this layer? For years, scientists knew that the dominant mineral in the lower mantle, perovskite, transforms into a new phase called post-perovskite under the extreme conditions of the D-double prime. This explained some of the speed change, but not all of it. The final piece of the puzzle, confirmed by recent experiments, is mind-blowing. Solid rock can flow. It's not a fast flow, but over geological timescales, the mantle convection slowly aligns the crystals of post-perovskite in the same direction. Think of it like the grain in a piece of wood. If you send a wave along the grain, it travels faster. This crystal alignment makes the rock harder in one direction, giving seismic waves a superhighway to race through. The long-held theory of flowing solid rock deep within the Earth is now a certainty. This layer is anything but static. It's a region of intense geological weather. It's believed to be the birthplace of mantle plumes, massive columns of hot rock that rise to the surface to create volcanic hotspots like Hawaii and Iceland. Those ancient iron-rich patches might act as insulators, trapping heat from the core until it bursts upwards as a plume. At the same time, the D-double prime is also a graveyard. When tectonic plates collide, the denser oceanic plate can be forced downwards, sinking all the way through the mantle until it comes to rest on the core-mantle boundary. The interaction between these cold, descending slabs and the hot, weirdly composed D-double prime layer creates even more chemical and thermal chaos. Within all this activity, scientists have found even stranger patches called ultra-low velocity zones, or ULVZs. These are thin spots where seismic waves slow to a crawl. The leading theory? These are the iron-rich relics of the magma ocean, which perfectly match the properties of these ULVZs. The exploration of the D-double prime layer is truly a new frontier in science. Every discovery, from flowing solid rock to chemical fossils of a magma ocean, paints a more complex and awe-inspiring picture of our planet's inner workings. Understanding this boundary is key to understanding everything from our protective magnetic field to the movement of the very continents we live on. It's a powerful reminder that even after centuries of study, our planet still holds profound secrets in its depths, waiting for us to uncover them. Thanks for joining us on G Fun Facts Online, and be sure to tune in next time for another deep dive into the wonders of our world.